For determining the cell potential and equilibrium constant, Nernst equation is used. Nernst equation is considered a general equation which connects the free energy and the cell potential. So, if you've got a reaction and you need to find the cell potential at any moment or under any condition, rather than the standard condition, we can use Nernst equation. Nernst is considered as an important relation used in determining equation constants and concentration potentials, besides calculating the minimum energy required in electrolysis, as will be shown later. In front of us is Nernst equation, whereas E represents the electrical potential, R represents the universal gas constant, which equals 8.31 joules per Kelvin per mole. T represents the temperature in Kelvin, which equals 298 Kelvin at 25 degrees Celsius. Z represents the valence of the charged particles, for example, sodium and potassium ions are positive 1. F represents Faraday's constant, which equals 96,500 joules per volt times mole. And finally, Ln represents the natural logarithm of ion in over ion out. Applications on Nernst equation, the galvanic cell. A galvanic cell is generally defined as an apparatus that generates electrical example of a galvanic cell. One of the interesting part of it is the flow of the whole ions instead of the flow of electrons. We've got two electrodes. The zinc electrode acts as the anode and the copper electrode acts as the cathode. In this case, wires connect the metal rods with a voltmeter, which connects the metal rods that are suspended in the solution of their own ions. They're the anode and the cathode. They're used from up the anode, moving from there as they are being oxidized and the metal slowly wears away. Meanwhile, the opposite happens at the cathode rod, where metal ions from the solution gain electrons and precipitate on the cathode as pure metal, gradually growing larger. The circuit is completed by a wire, but also by a salt bridge, which is a U-shaped tube that contains a salt solution suspended in a gel that allows the metal ions to move from the anode to the cathode. The standard reduction potential is the tendency for a chemical species to be reduced, and it's measured in volts at standard conditions. The more positive the potential, the more likely it will be reduced, and vice versa. For the redox reaction to proceed, the difference in the E nodes of the reacting systems must be greater than or equal 0.2 volts. One last point, the hydrogen half cell equals 0. In this galvanic cell redox system, we have two electrodes. The copper electrode will act as the anode, as oxidation happens in it, while silver electrode acts as the cathode, where reduction happens, with the presence of salt bridge. By writing the shorthand rotation method, it appears as the following. The copper metal loses 2 electrons and changes into copper ions, and silver ions gain 1 electron to change into silver metal. In redox system, the number of electrons entering must be equal to the exiting electrons. The copper lost 2 electrons while silver gained 1 electron, so we must multiply the silver half cell by 2. Moving on to the next step to calculate the cell potential for the whole cell by using the electrochemical series. The electrolytic cells are actually the opposite of the galvanic cell, whereas they're an apparatus in which an electric current causes the transfer of electrons in a redox reaction, which performs electrolysis, which uses electricity, electro, to do the breaking part, lysis, where it depends on a power source because it's a non-spontaneous reaction. Electrolytic cells have an endothermic reaction where energy is stored in an electrochemical cell, which can be released if it's allowed to run in a galvanic mode. In this case, The molecules in the solution are being broken down so that the metal can be deposited on the surface. The reduction potential must contain oxygen to be affected by the pH, which is the first factor we have affecting Nernst equation, whereas increasing the acidity of the medium by increasing the concentration of the protons leads to increasing the electron potential and decreasing the pH, and vice versa.
We've got two beakers containing two solutions. The pH in the first is 3 and the second is 5. Since the pH is known, we're going to increase the concentration. By increasing the concentration, the acidity increases. Because of the high concentration of the protons, the pH decreases and the potential increases. Say this one decreases into 1 and the potential increases because of the increasing of the protons. Here the pH decreases to 3 and the potential increases, and as the protons increases, even though both pHs decrease, the electron potential in this one is higher.
The second factor is complex formation. Some substances form complexes with each others, just like the phosphate and the ferric ions. When the complex is formed, the concentration of the ferric ion decreases, so the potential of the system decreases, because the concentration of the ferric ions is directly proportional with the potential. Or a soluble complex may be formed, a soluble complex of mercury chloride with the iodide ion of tetraiodmercrate, whereas the concentration of the iodide ion decreases, so the potential increases, because the concentration of the iodide ion is inversely proportional with the potential.
A flask containing tetraiodmercrate, then we're going to add mercury chloride to the flask. A soluble complex is formed with the iodide ions, which leads to decreasing the concentration of iodide, by which increases the electron potential.
And finally, we have our last factor that affects Nernst equation. It's called the common ion effect. Adding manganese sulfate to permanganate solutions leads to increasing the concentration of the manganese ions. And on the other hand, the potential decreases because, as we see in the equation in front of us, there's an inverse relation between the concentration of the manganese and the oxidizing power.
A flask containing a permanganate solution, we are going to add manganese sulfate, which leads to increasing the manganese ions concentration, thus the electron potential decreases. And by looking at this equation, since the E potential is inversely proportional with the manganese concentration, by increasing the manganese ions concentration, the electron potential decreases.